Assalamu alaikum wa rahmatullahi wa barakatuh. This is Dr. Ali El-Moursy, and this is our first online lecture for Digital Logic Design DLD. We will be covering the following material, the rest of Chapter 3 and Chapter 4 through the online sessions. And this is the first session that I'm recording for that. As you can see, I have uploaded a, detailed schedule for the class week by week, not only week by week, but lecture by lecture. As you can see from the slides here, actually this document for the lecture material, which I will show right now, is actually available on the Blackboard for all the students. And it actually shows the material that we are covering lecture by lecture. We are actually at lecture number 15. We already covered in the class for the chapter of the K-map, the NAND, the NOR gate, discussing one type of logic gate simplification, which we call it the multi-level NAND and the multi-level NOR. In this lecture and maybe another recording, so in this recording and the next recording, we will we already covered in the class the NAND gate and how can I convert any of the three basic logic gates, the AND, the OR, and the inverter through the NAND gates. And in the lecture of today, we have three things to cover. How can I do the same table of conversion between the three basic logic gates AND, OR, and inverters, but through the NOR instead of the NAND, which we didn't cover in the last lecture. So this will be covered in this lecture. Also, we will cover the two-level NAND and two-level NOR. What we covered in the lecture is multi-level NAND and multi-level NOR. If the time allows in this session or maybe the next, we will also cover the XOR, which is one extra gate that we didn't discuss or studied yet. Don't care is already covered. Okay, so we will learn the XOR, 2 input and 3 inputs. It's truth table, it's K-map, and different equation formats for the XOR. So let's start our lecture. And as we did for the NAND, we need to actually to see how can I convert any logic gate, basic logic gate, and the OR and the inverter through the NOR. First of all, we need to learn what is the NOR gate. As usual, we are learning a new logic gate, so we need to learning new logic gate, so we need to define the new logic gate. We need to see it. We need to know the three basic components of the logic gate. So we have our table that actually shows the three things that we learn in any logic gate. We learn the gate symbol, we learn the equation, we learn the TT. For the NOR is actually a not OR. Since it's not OR, okay, so it has a shape similar to the OR gate. So it looks like the OR gate, but it has a small circle in front of it that actually indicates that I have a negated logic. So if I have input A, input B, the output will C. I can represent this gate also as C equals to A or B or 2 bar, as if I have an OR gate followed by an inverter. The truth table, the TT, for this gate looks like any TT, inputs, outputs, A, B, and C. I have two inputs, so I have actually 4 rows, all possible combinations of inputs, 0, 0, 1, 0, 1, 0, 0, 1, 1. And the output is, since it is NOR, not OR, so I have 0. Or NOR 0 is 1, 0 NOR 1 is 0, 1 NOR 0 is 0, and 1 NOR 1 is 0. So it is a negated logic for the OR, which is called the NOR. Then, after we learn the NOR, we need to build our second table, the table that actually shows me how can I convert from the other 3 basic logic gates, or representing the basic logic gates through the NOR. So we have 3 basic logic gates. We have the AND, we have the inverter, or not, and we have the OR. Can I replace any of those logic gates using the NOR? The answer is yes. And here I have 2 representations. I can do this either through the circuit or through the equation. If I ever have an AND gate and I want to remove it and replace it with a NOR, this can be represented in the equation as x, y, and z. So I have z equals to x ended with y. Okay, so x ended with y. If I want to represent it using NOR, I have to put 2 bars, and I will break the inner bar using De Morgan. So I will get x bar or y bar or 2 bar. Only the inner bar will be broken, which will give me x bar or y bar. Now I have a NOR, but a NOR between the x bar and y bar. So the equivalent for the NAND, for the AND, is actually a NOR gate, but I have to put inverters at the inputs of the gate. Okay? So for the OR, if I ever have an OR and I want to remove it and replace it with a NOR, so the same thing, the same concept, x, z equals to x or y. Here I will put 2 bars and no need for breaking the inner, because actually the inner here representing a NOR followed by an inverter. So accordingly, the circuit will be a NOR gate followed by an inverter. This is the equivalent. Okay, equivalent for AND is an OR and two inverters at the inputs. For the OR, it's an OR and followed by an inverter. As we mentioned in the lecture, if I have an inverter and I want to represent it using NOR, so the inverter will have the equation of X equals or Y equals to X bar. Y equals to X bar. So Y equals to X bar, and from the Boolean algebra properties, X or X equals to X. So I can replace it X with X or X. So that means I can convert the inverter through a NOR gate. Okay, both its inputs connected to the same input. Okay, so this is the table of conversion, and in the next lecture we will learn how to use it in one of the examples, the example that we learned in the class, in order to have what we call a multi-level NOR circuits. This table will help me in multi-level NOR and what's called also a two-level NOR. Okay, so let's take a little bit of break and then we will continue with the example of how to solve such a problem.